We have here at the CLAPEM. We have the pleasure to have Professor Fernando Quintana from the Pontificia Universidad Católica de Chile. He is one of the best people in the world to work about random matrices, random partitions. Otherwise, you're going to ask him for some things. What can I say about him? Many things. Many of us around here, I think we know him well. But one good news is that he's the new chair of Bayesian nonparametrics section in ISBA, so one of the most prolific sections of ISBA. And yeah, he's going to talk us about on some classes of random partition models with applications. So I would like to welcome him. Thank you.
Thank you, sir. Okay, well, thank you so much for the extremely nice and I think undeserved introduction, but well, thank you anyway. So this is supposed to be, as they asked me, a sort of like an overview with some old things and some new things. So I'm going to start by giving a little bit of background here, reviewing a little bit of the notation, some of the models that have been proposed, and then I'm going to introduce something that I've been working also on, which is the notion of repulsion, and then I want to finish with some more applications. Finding interactions, this is something that is kind of like being developed right now, and this is also another application that I've been working on recently. Okay, so let's start with the beginning. So just to set up the notation, so here is a set of indices, just 1 to n, and a partition of them, of this set of indices is just a collection of subsets that are supposed to be non-empty, each of them, and mutually exclusive, so nobody gets left out. So the number of partitions, of course, is a huge number. Here's just the exact, the number of them is this Bell number. With 5 elements, you get 52, and all the way to when you have 100 of them, you have this hard to imagine number over there of possible partitions. Now, in order to work a little bit with these things, so with the typical trick that we do here is to introduce these class memberships. So you say that the element I belongs to subset J. Sorry, the Ci equals J means that the I belongs to the subset J, and that's another way of representing these things. Sometimes we have, of course, in applied problems, we have measurements, some responses and covariates, and we need to refer to the subset of responses and covariates that belong to a certain clusters. I'm going to use the star notation to denote that. Okay? All right. So what is a random partition? A random partition model is just a probability distribution on the set of all possible partitions. That's it. Okay? Now, in the way that I became interested in these things is through Bayesian nonparametrics. In Bayesian nonparametric models, when you have a discrete model for the random distribution, and here is like a prototypical, like a standard way of setting up a BMP model. So you have some likelihood with conditional independent assumptions, and then you have some parameters that are drawn from this distribution G, and then you put a distribution on G, and that's the BMP way, typically. And this is a famous way of doing that. I'm not going to say much more about that, but just point out the fact that this is a discrete distribution, okay? Now, if you have that, then because of the discreteness, you'll have things that are repeated, okay? Because you're drawing these parameters from this essentially discrete random measure. Some of these values are going to be repeated, and if they are repeated, you can now play the game of identifying which are the unique values, and then you look at each parameter for each individual and see to which of these values it's assigned, and then you can represent a partition of your set of indices just by identifying these values, these unique values. And that's that's one way in which random partition models arise. And I stress here that this is an induced partition model. All right. This is an interesting property if you are concerned about certain fundamental things. One interesting property is that the model for a partition with n+1 objects. If you marginalize the last one, it gives you back the model for n. And that's something that's called the sample size consistency. All right, more generally, one can describe these or some classes of random partition models by looking at what is called the exchangeable partition probability function, or the EPPF. And that is essentially a function defined in the unions of all these k tuples from k equals 1 up to infinity. And they have to satisfy this property, P of 1, when k equals 1 is just 1. And then there's this property of marginalization from n+1 giving you back the model for n. And if this function satisfies these properties, it's called an EPPF. And then a random partition model arises by simply saying that the probability of this particular random partition is just the PPF evaluated at these, the cluster sizes. That is a random partition model, and it satisfies these properties. Okay? All right, so if we go back to our BMP model over here, what happens is that it's not always the case that you can write down a formula for the induced probability of the partition, but there are some famous exceptions. One of them is the directed process, for which you get this particular expression. Another famous example is the Pittman-York process, which is you can view this as a generalization of this formula, because if you take alpha equals 0 over here, you get back to this exactly same expression. But there are combinatorial interpretations of all of these things. And there is a further generalization, which is called the class of Gibbs type priors. In a sense, they can be seen like the connecting line goes in this way. Okay, so this is a particular case of that, and this is a particular case of that, and that's something that's been studied in these two references over there. Okay, now another way of looking at these things is by thinking predictively. So if you want to, the predictive view is to say I have some certain number of individuals already assigned to partitions, and then I want to ask the question, okay, so what do I do with the next one? Where do I place this next individual? And the typical thing that happens is that with some probabilities you will assign this new individual to whatever clusters you already have, or you will have a probability of creating a new one. And that's described by this prediction probability function, or PPF. It's not the EPPF, but just the PPF, okay? And if you have an EPPF, the predicted probability function is simply computed. That's the probability of, the entire partition with the next individual divided by the probability of the partition of the first n. Now, if you look at the Pittman-York process, you get this formula over here. And if you look at the Dirichlet process, you get this formula over there, which is, again, obtained by setting alpha equals 0 here. But then this is what typically is referred to as a Chinese restaurant process, with this probability of joining a certain cluster being proportional to the cluster size, and the probability of forming a new cluster is proportional to this parameter over there. When you have the Pittman-York process, you have a certain change in these formulas, and the probability here of joining a new cluster, an old cluster, is decreased a little bit, and this is why the alpha is sometimes referred to as the discount parameter, or maybe because of that it's called the reinforcement parameter also, but I mean there's a difference between these things, okay? And then you can write this formula explicitly for some other more general processes, but it's not necessarily the case that you can always write this for any arbitrary random process, okay? All right, so parallel way of going through this, something that I've been working on also a little bit, is to simply just write down a formula. If you want a probability model, just write down the formula. That's it. But of course, you might lose this sample size consistency property, which is something that may or may not bother you if you don't ever need to predict then you just have a formula and work with that. But if you want to predict and you want to think that there will be more units coming in the future, then you want to worry about that. Okay. So the product partition models is a famous class of models that have been used for this particular purpose. What is called the parametric PPMs are defined in this particular way. So you have like again like a sampling model. So given the parameter that's attached to the cluster, you have IID distribution, the IID observations, and then your parameters, your unique values are sampled from a certain distribution over here. And then you have a probability distribution for the partition, which is written in this product form, and this is why this is called the product partition models typically. And this value over here, this is a function of the cluster. It's called the cohesion. And you can actually set up here whatever value is. This is just supposed to indicate how strongly you think the elements in this particular subset are going to be together. And of course, you can play the same game by referring to the cluster membership indicators. Okay, so this is the product distribution, this thing over here, and the normalizing constant is just you have to divide by the summation of all these formulas to get a probability there. One famous example, and this is why I became interested in these things, is that if you take the cohesion function to be like that, you get exactly the same formula as in the Dirichlet process. Okay, it's exactly the same. So you can think of the Dirichlet process as giving rise to this product partition model after integrating out the random measure part. And if you do that, you get exactly to the same kind of models. All right. But of course, the limitation is that I said that in principle you can define this cohesion function any way you want, but there are not many choices where you will get something that is a valid ePPF. All right, so that's a limitation of the approach. Another related approach is just by resorting to finite mixture models. This is like the typical finite mixture model. You say that my data arrives from a certain, mixture of distributions. These are the mixing weights, and these are there are several parameter values that can be giving rise to your data. And that's, for instance, you have normals, you have something that looks like this, like wavy distributions. And this is a standard way of setting up this with a Dirichlet distribution for the joint distribution of these parameters. So an induced partition model has been studied, and here's an explicit formula for, and it appears in this paper, resorting to these increasing and decreasing factorials, that you get something like that. You may have a prior distribution on the number of components, you may or may not. That's something that some people use and some people don't use. If you use, then you have to deal with the varying dimension things. So you have to go into reversible jumps or any sort of transdimensional method. But anyway, or some people prefer to just choose a large enough K, and then you work with what is called the overfitted mixtures. All right, that's another way to proceed. But in any case, this gives still a valid ePPF. Okay, so some extensions before going into some more applications. So some extensions of this. Of course, the partitions can be thought in different contexts. One particular context that has been used in the change point literature is to think now that partitions are actually in blocks, of consecutive blocks. Rather than any subset that might be disconnected, you think that there's blocks of things that are consecutive, and a new subset is just a new block. All right? So, and that is, I guess you can imagine why this is called it's good for change point, because exactly the points that mark the beginning or ends of these blocks are the change points. And typically inference, is focused on detecting where these things happen. Barry and Hartigan were the ones starting these random partitions in blocks in the product form. And Rosangela Losky and co-authors have worked a lot on this particular topic. But then you can think of more elaborate ways, like you have more than one population, like more than one set of indices, like if you had 2 samples, and you want to do something that somehow combines these things. And you might think of models that where some of these things are sharing some elements. And there's a very nice paper that's going to come up in Bayesian analysis that describes something that is called the partially exchangeable PPF. So if you're interested, you may go into the Bayesian analysis page and look for this particular paper. Other type of extensions is now we want to play the game of thinking of these partition models, and in the case where you have covariates, and you would like to have the situation where your individuals, certain individuals that have similar covariate values are a priori more likely to be clustered together. All right? So that's one particular thing that I've been working on, and this is actually related to the notion of nonparametric regression. In nonparametric regression, you have a collection of random measures indexed by a certain predictor set, and you want to put a prior distribution on the whole collection. If you do that, and these things are discrete, then you can think of that for every x, I have a discrete random measure that will create my partition things. So I can have partitions that somehow move with x, in a sense. Okay? And that's exactly what we try to do from the product partition model angle in this paper over here. So what we need is to take the product partition, the product distribution that this is just the product of the coefficients, but now we add something that an extra term there that we call the similarity function, and the similarity function is supposed to measure the homogeneity of the covariate values for those individuals in that particular cluster. And the idea is that the more similar these things are, these covariate values are, the higher this similarity function is going to be. All right? And there are several particular choices that you can use, and you can adapt these expressions for the case of continuous covariate, discrete, ordinal, et cetera, et cetera. And you can even think of these things as coordinates, like your reference coordinates, and we have done that in a paper that appeared in Bayesian analysis a few years ago. There are extensions of this, of course. Park and dance on this variation of the PPM by simply taking a more general function of the cluster and the covariate. There is this distance-dependent Chinese restaurant process where the table or the cluster assignments depend on the distance between the measurements. David Dahl has this very clever idea of taking the Pittman-Yor probability distribution for partitions, but now what he does is to internally reassign measurements according to a notion of distance. So the marginal distribution of the partition is kept intact, but how things are arranged inside the partition changes according to the x values. This is something that is coming up in JASA, and this is a very, very clever notion of a location scale random partition model. So you have a partition, and then you think of a location model and a scale revolving around that particular partition. That's a very clever construction. This is another paper that you can find in an archive where they use the notion of centering process, where you have a partition model again centered around this particular partition, and this is good in the case where you have prior information on a certain partition that is prominent for some reason. Okay, and then you have a model. You want to have a model that varies around that. Okay. All right, so I think this is the first application. So the typical thing with all these partitions, of course, is many people do clustering. And there's lots of clustering applications. Well, let me just state the obvious first. If you have a prior on the collection of partitions, then you have a posterior on the set of partitions as well. All right. So, but then the natural and obvious and hard question is, how do I find a partition? How do I estimate one? This is, of course, this is a very old problem. There is lots of algorithmic options there. I'm not going to go through the algorithms here. I'm actually more concerned about principled ways of doing this problem. So essentially what we have is a posterior distribution on this huge collection of remember the Bell number that can be extremely large even when you have 100 of points. So you have a collection of all those potential partitions and you want to summarize one. Okay. So if you want to do that, there are a few options. There is a paper by David Dahl discussing what is called the modal clustering, that is trying to estimate somehow the partition that is most likely a posteriori. So it's like a MLE in a sense. And then there is this other option where you define a loss function properly, and then you want to optimize that loss function. And there are a number of options there. Binder has a 78 paper that has been sort of like revisited here. And this is something interesting because once you have like a point estimate, the typical thing that we want to do in statistics is to have a notion of uncertainty attached to it. And there is a paper by Sarah Wade and Gramani describing point estimates and credibility balls around these point estimates. If you want to have an idea of further ways of summarizing the posterior distribution of partitions, this is a paper that is, I suppose it's available in David's page. All right, so here is an example. This is an example I did a few years ago, but I think it's interesting because it's, this is the basketball data, the NBA. So you have, there is something called the Hollinger game score, and the Hollinger score is just a complicated function of a number of the number of assists, the number of rebounds, the number of points scored, the number of triples, etc. And there is a game per game score attached to each player, all right? And here's sample data, the data for three particular players with different positions. So what we have here is just a bunch of points. Look at the spread of here, it's quite different from there and not exactly the same as there, but you have a collection of points, and the idea is that we want to cluster players based on that in particular information. The red curves here, I think, correspond to some sort of lowest, like a local regression sort of curve fitted. But going back to our target, the target here is to cluster these players based on these scores. Now, the clusters are going to be based on curves, okay? So we're going to have a curve describing each of these evolution of the scores. But here's the trick. If you want to have a very good curve profile for each player, then essentially all these players will be different. And your estimated partition will be as many subsets as individuals. That's not used. On the other hand, if you want to, borrow too much strength and smooth too much, you will essentially end up with something that looks like one or two maybe clusters, and that is no use either. So the challenge here is to think in terms of clusters being defined as curves, but then what we're going to do is to have the clusters are going to, the clusters are defined in terms of these, sort of like curves that are common to this subset of players, but then on top of that cluster-specific curve, we'll have a little variation and will allow the player-specific curve that wiggles a little bit around this cluster-specific curve. So the point here is that you want to still have something that reasonably fits each of the individual profiles, but we want to borrow strength across different subsets that might be, if you look at the mic with a zoom or with a magnifying lens, if you want to look at particular features, there might be, of course, differences, but you want to somehow borrow strength according to the shapes of these curves. And that's the purpose of this clustering application. So I guess I kind of like said that already. So there are player-specific curves, but there are cluster-specific shapes. And the curves for the players wiggle around a little bit around the cluster-specific shapes. And then we have also some covariates. If you are into basketball, you will recognize, for instance, this is the draft order. It's kind of like players that are valued when they start the league. They are, sorted and ranked and drafted according to their particular abilities. There's the experience, whether these players played before or not in the high school basketball or something like that, and then there's the age during the first game played. All right? Okay, so I'm not going to give details of the model because it would take me too much, but I just want to point out that these are, so we found, I think, something like 18 clusters with the players. And these are some of the, these are the 9 most populated clusters. You will see here what we call the role players are like players that are, I don't want to say something that might be demeaning to them, but they are kind of like average people, supporters, supporting cast. Let's say it that way. And here are some of the stars, for instance, this guy, LeBron James, a very famous one. He's Shaquille O'Neal, of course, Kobe Bryant, etc. So what you see here is players being grouped in terms of these shapes of the curves. For instance, these players over here are kind of like, you can see, they are kind of like keep increasing in terms of this score. Players over there start high, but then kind of like start declining, and then there is, different variations in terms of here players that start slow, improve, and then start declining, etc., etc. All right, and here there's a kind of like a smallish cluster. All right, so there is these dotted lines here or dashed lines that I didn't explain much, but there was a further complication. The further complication is that not all players have their careers finished by the time we, this is our data set. And so we also consider the prediction of what's going to happen to them eventually. But that's a further complication of the model. In any case, I want to use that as a starting point for talking about repulsion, because you can see these are the most populated clusters, and then there's this kind of like a small one over there. And something that happens quite often is that when you try to estimate partitions, you might end up with subsets that are very small, even singletons. And the problem is that what to do with a singleton? I mean, what interpretation can I give to a singleton? It's very hard to interpret, all right? And one of the reasons why that happens is that the typical models we use assume that when you have these parameters that characterize the clusters, these parameters are coming IID from a certain baseline distribution. Now, think in terms of a normal. If you have, and draw 3 or 4 values from a normal, what are you going to see? You're going to see that they kind of like to be in the zone where most of the mass is concentrated. So letting them to be IID, it just opens the room for them to be arbitrarily close. And if you want to get rid of singletons or very small clusters, what you would like to do is to push them apart somehow. And that's the notion of repulsion, okay? So here's this is simulated data. It's totally non-interesting, but I just want to point out something. So this is simulated data from 4 bivariate normals, 300 observations. Here are the simulated values according to a particular component. And on the right-hand side here, what I did is to feed a DPM, a direct process mixture model, and estimate the partition using some of the methods that I passed very quickly recently. But here's what happens. So there are the truth contains 4 subsets, 4 components. And here we estimated 6, okay? All right, so the 6 is not so much an issue, but this particular thing over there, this is a singleton. Okay, so and what I'm describing here is not uncommon at all. You will, whenever you try to estimate, get a point estimate of partition, you will often get singletons. And so the problem is, how can I get rid of that? Well, so the solution, or one solution, is the notion of incorporating repulsion in these partitions. And I guess this is I just told you that. The prior, that has IID components allows them to be free to move, so they can get as close or as they want with no particular restriction. There are a few methods over here that describe the notion of repulsive mixture or non-local priors. These papers are, I think this is just appeared recently in Royal Society B. Or you can use point processes that have the ability of repelling things. Determinantal point processes is one particular option. Another one is just to have an explicit construction of a notion of repulsion. Here, what we have is a joint distribution that has 2 parts. The first part is the usual IID thing. Okay, so a product of densities evaluated at the points, that's your IID part. But then we add this component over here that has the property of when the distance between these 2 different vectors is small, the value of this function goes to 1. And if the value of the function goes to 1, 1 minus 1 gets very small. So the joint density decreases when these things get close. Otherwise, if they get far apart, you simply let this function go when the argument goes to infinity, get to 0. So if they are very far apart, this essentially is 1, so you go back to the independent case, right? So that's a possible way of introducing the notion of repulsion. And it has interesting properties. I don't really have time to discuss that, but with finite mixture models, if you have a large enough number of components covering the true number of them, and if you choose the different prior for the weights in a certain clever way, there is a paper by Judith Rousseau and Gary Mengersen describing what happens with the overfitted mixtures, and asymptotically things are okay. So you estimate that you recover the posterior concentrates around the true number of components, assuming that number is smaller than the whatever k you chose there. Or, but in our case, I think there's also good properties, and I think we can show that the notion of repulsion helps getting to the truth faster. I'll just say that because I don't really have time to go into details. So what I did is to here is to take a model like that using bivariate normals as our kind of like the IID part, and using some kind of exponential definition here, and fitted this repulsive model and estimated the partition again. And what happened is that this singleton is not there anymore. So we kind of like we got rid of the singleton by using this notion of repulsion. And the number of of subset that we estimated is 5. It's still not 4, which is the truth, but still, but it's closer to the truth than the other case with the IID cluster centers. All right. Okay. So in the final part, I will describe two applications. So finding interactions. So this is just, if I say the word interaction, I guess one of the things that we learn in our undergraduate courses is that if you have something like a design of experiments, an ANOVA setting, and you compute the averages of the combination of factor levels, and you plot those things, and you see something that looks like an X, you say, oh, there's an interaction. And if you see something that looks like parallel curves, you say, oh, no, there is no interaction. All right? That's the kind of like a undergraduate idea of interaction. But then, let me go a little, let me take this idea a little further. Let's assume that we have two factors here, A and B, with two levels each. And let's suppose that the true distribution that corresponds to each of these combinations are plotted right there. So there is a normal distribution, there is a t distribution, and there are two mixtures of two normals. But all of them have mean exactly 0. So if we were to look at just these averages, we'll find that there is no interaction because they are all 0. So you'll get these parallel lines. But of course, the distribution of the responses is different across combinations of the factors. All right. So that's the idea of what we are trying to get here. The notion of interaction is something that affects the distribution of your responses in some way. Okay? All right. So this came from an interesting data set on acute lymphoblastic leukemia. As with many of these cancer-related diseases, the treatment is this radiotherapy, and the radiotherapy is like it's like a kill them all approach. You know, it kills the bad things, but also kills good things. And one of the side effects of that is the occurrence of this thing called the osteonecrosis. And the osteonecrosis means that the bone tissue dies because there is not enough blood getting to it. So in an extreme case, it may actually require joint replacements, which is something that it's quite serious. Plus, these are children. Okay, so it's twice bad, I think. Twice as bad. All right. So what we want to do here is because the data set I'm going to describe it in a minute, but we have several covariates. And there is the suspicion that things are interacting in some complicated ways, but there's not really much notion of how they interact or what to put in an interaction term. If you're thinking in terms of building a model, what to put there, all right? And then, furthermore, the notion of interaction that we are trying to set up here is something that, you know, some combination of covariance that influences the response in some way. It could be changes in the expectation, it could be changes in the variance, it could be changes in the shape, or all of them, some of them, etc. We don't really know. Okay, something that creates changes in your response. Okay, these are the responses are ordinal. It's a degree of severity of osteonecrosis goes from 0 up to 4. 0 is the mildest, 4 is the highest level. So most of these children are in these first two mild levels. But in any case, there are 234 observations and 22 predictors. Of course, if you think in terms of a saturated model, that would be like a huge model. And it's kind of like quite unreasonable to think of this huge model. Furthermore, there is particular interest here in the interactions between these two drugs and the other things. And so I'll use that explicitly in a minute. But in any case, what we want to do here, our ultimate goal is to be able to say in some very general way, identify which covariates are creating these interactions, which covariates are the most relevant in terms of, you know, affecting the distribution of the response. All right, and I say exploratory because After we explore this, we can point the physicians in charge that there's something that might be potentially interesting to further explore. Or as statisticians, we want to say, okay, look, keep an eye on this particular subset of covariates, and the others, are not that relevant. Okay, so in a sense, sounds like variable selection, but this is more general because I'm going to show our model doesn't include any term in the likelihood at all. It's all done through the prior. All right. Okay, so what we have is a procedure that has 3 parts. One is to connect the covariates and the response using a random partition model that depends on the covariates in the prior. We're going to use the PPMX model, so the product partition model with the similarity function that I described earlier. Yeah, but the goal here is to look at clusters and how these clusters are formed and how the covariates are, being, or what role the covariates play in the formation of that particular cluster. That's the way we're going to, our angle into this. Then we're going to look at the particular clusters and see which of these covariates are more important in the formation of that particular cluster, which ones are anchors in a sense. And we're going to use the what is called the association rules. It's a technique borrowed from machine learning. Kind of like feels okay borrowing stuff from machine learning. It's typically not exactly how it works. So the main thing is that these techniques are very efficient. And there's even a package in R. It's called A-Rules, I think it is, that has implementation that is efficient. So basically, what we do here is to find combinations of covariates that are more frequently observed in that particular cluster, all right, that are more prominent. Of course, there could be high nonlinearities here, all right? And then we're going to ask the question, okay, so we select these subsets of covariates that might be relevant for describing what creates changes in the response, and we are going to actually test for that. Okay, so it's a formal test procedure. So is there an interaction or not? Okay, so that's the point. Because sometimes you can have false positives here. I mean, you can have things that look like they're influencing, but they are actually not important in that sense. So we are going to use a procedure based on Polya trees. And this is the source that we, Chen and Hanson, that we're using for this particular procedure. All right, so our response is ordinal, so we're going to have the typical latent score model. In the latent score model, we have certain cutoffs. There is a good reason why we take the cutoffs as fixed. I don't really have time to go into that. But then we have a, given the latent, the response is completely deterministic. Okay, so the model goes there in the latent part. Notice we have absolutely no X here, and then this is just a normal distribution in each of the possible clusters. The parameters are sampled from this particular distribution, and then we have our PPMX, product partition model with dependence on covariates in the prior, and that's it. That's the model. All right. So I'm going to skip forward. There is no time to go into the details of that, but essentially, running the procedure with all the parts that I described gives us a list of interactions. These are certain combinations of covariates coming from the association rule. The support and the confidence are the association rules, by the way. This is the average cluster size where we found that, and this is the percentage of the MCMC iterates where the interaction was found, and this is the final value of the p-value for the Polya tree test. As you can see, there are indeed some false positives according to that. But in any case, there's a summary of the things that interact with each other. Now, what we did here is to look at the posterior predicted probabilities of osteonecrosis involving these combinations, some of the combinations of the predictors we found. And you see the highest levels of the osteonecrosis are found in some combination of this low level of the DEX drug. But the particular, how this happens actually depends on the combinations of albumin and cholesterol. So that's an indication for us that there might be a three-way interaction between these things. And we actually specifically went back and tested for that and got a positive answer. And this is kind of like exciting because it was something that was not previously reported or discussed. So we can go back to the physicians and say, hey, look at the combination of these three things that might be relevant for studying the osteonecrosis. So how much time do I have? 7 minutes, okay. So I think I have enough time to at least describe what the problem is here. So this is a subset of data on a math score that is performed regularly in Chile as a way of measuring the quality of education. This is a average per school in my city, in Santiago. And the values are, I think the max is 300 or so. I might be wrong on that, but in any case, you can see that the high values tend to kind of like be mostly over here in that area. This is like the northeast part of Santiago. And what you see here is that if you go from one year to the next and to the next and to the next, you see that the scores tend to, the average scores for schools tend to, be consistently, there are not super many changes over time, all right? And also, that's one thing. And the other thing is that there seems to be some kind of a spatial effect. Like there are groups of lower values, there are groups of higher values, and these kind of like, remain over time. So that motivated us, and this is just, I took one example of a few schools, I think it's 6 or 7 different schools, and we followed them through time. You will see that there are some cases where there is a little trend of increasing thing, but here is another one that decreases and then remains low, and then there are some like ups and downs over there, like this green. So there seems to be correlation as well on time if you focus on one particular school. So in any case, what we did here, just an exploratory thing, is to run our clustering procedure for each school, for each year separately, and these are the estimated clusters. So what we see is that these clusters are very sticky on time. All right, so they remain quite stable, and there is also a quite substantial spatial effect. So that motivated us to come up with a model that can cope with the case where you have sequence of partitions, where the partitions do not change a lot from one time to the next, and they also have some spatial structure. All right, that's the goal. I think I will skip that, but there's a quite substantial literature on non-parametric Bayes going related to time and space models. This is a super important paper over there in the time thing. You can ask Michele later about that if you want. But in any case, so our goal is to provide a construction of partitions that evolve in time and space later. And the idea is to have this control over the temporal dependence, okay? So allow things to change a bit, not super much. All right, so the way we do that is by building a joint model for this collection of partitions, and we do that in a sort of like Markovian way with a certain ePPF model for the first and then variations on that. And the basic construction we're going to use is something that I guess heuristically can be described by saying that there will be a certain subset of elements that are frozen or pegged, that would be the way to describe it. They are fixed, they don't move, but the rest are allowed to recluster from one point to the next. Okay, so that's the idea. And then there's these parameters, these gammas, that indicate where they are pegged or not. And there is a Bernoulli distribution with a parameter that's time period specific, describing which of them are pegged or not. And then, of course, these two extreme cases, if everything is pegged, then nothing moves. So you have the same literally the same partition. And if nothing is pegged, then you have partitions that are completely independent one of the other. But what we want is somewhere in the middle, okay? There are other constructions that do similar things, but they allow the relocation of every individual, so they lose this property of being smoothly transitioning from time to time. There are some good properties if you do things in an interesting way. You can actually show that the model for a time t is the same as the parent, the model for the first one, using properties of these ePPFs. This is just I will skip the simulation. Essentially, we're going to use a model that has the spatial locations. There is a spatial component. There is a time trend that is allowed, and this is the prior on the partitions that has the ability of incorporating spatial information. And that's it. That's our model. So there is no spatial component in the likelihood, and that helps us, avoiding this problem of having these potentially huge correlation matrices that you have to invert. And so we avoid that. So this is the particular. This is you will recognize this is as a Dirichlet process kind of cohesion function, and this is the extra similarity term. Okay. And this ensures that the margin is maintained, and we call this the spatial temporal dependent random partition model. Okay, so I guess I already said that the model includes some autoregression effect for each particular school, but the rest, and there is I don't really have time to describe the model in detail, but there is a regularization towards zero independence just to try to control the size of the number of parameters that we have. And we have our partition model with some beta distribution for these alpha parameters. And these are the results. I think I will stop here, essentially. So what we have is, this is for the complete data set for 7 years. You'll see there are lots of well, the colors are not maintained, but you will see that there are bunches of clusters that are essentially very similar over time. And I guess you won't be able to see it much, but this is the estimated value of the posterior mean of the alpha parameter. So all these values are kind of like high, except for the one over here. From time 2 to 3, there seems to be something changed because the probability of pegging decreased to 0.7, but actually most of the time it's over 90%, which means that there is a lot of things that are being maintained. So there is quite static in terms of the partitions. I think I'll stop here. All right. Thank you very much. Okay, okay. I will stand next to you. Okay, screen.
I have a couple of questions. So one is a clarification on the alpha t. Here, the alpha t is IID from a beta.
From a beta, yes.
Yes. Could you include the temporal dependence or spatial dependence in the alpha t?
Not in the alphas. Not in the alphas. Okay, so one of the many things that I didn't tell you is that we did allow for temporal dependence in the baseline distribution of all of these models. So there is a normal likelihood, and then the means of these normal likelihoods are allowed to have some temporal structure, right? But the alphas, no. The alphas, no. They are supposed to be independent of.
And the second question is related with the nested models. You mentioned that with the paper by Camerlenghi, and I was wondering, is there anything like nested models in nested product partition models?
Not that I know of. I mean, it would seem like a nice project for somebody to work on. So we, yeah. So for that particular model, I mean, that came from the discussion, session that you organized in ISBA. And there is this paper by Camerlenghi and others comes with a series of discussions. So they were trying to fix one of the issue of the nested DP, which is another non-parametric model that tries to borrow or share things across different subpopulations. But they found that they had this property of if there is one atom that is in common between two subpopulations, and then the entire thing is forced to be essentially identical. If you think now, only in terms of partitions, it's hard to think of how one could, collapse one partition into another one that's exactly the same. But still, that doesn't stop you from trying to borrow across different subpopulations at some level. It's not obvious to me how to do it, but it sounds like an interesting project.
Yeah, because I was thinking also in your spatial-temporal example at the end, you could see that as a nested model.
Absolutely, but we didn't go that particular route.
Some other questions? I do have a question. When you deal with the posterior or the model-dependent covariates, you have a space of covariates, and you have also the space of the observations. I think you denoted like sets. Don't you have an identifiability problem there on the posterior, because the posterior won't be exchangeable, won't be consistent anymore, right?
Yeah, but that's a posteriori. I mean, that's given your data, and that's it. So the typical thing is that you a posteriori don't care super much about the whole collection of partitions. You try to actually sometimes you don't even care about the partitions themselves. But for instance, in predictive inference, you will integrate them out anyway. So
okay, so you're thinking just like a summarization that sort of runs over a set of partitions that you are care.
Exactly.
Okay, well, thank you. If there are no more questions, let's
Thank you
thank
for your
again
time.
Fernando.
Thank you for your time.